So I'm going to kind of flesh that example out here by sketching what I call a charge diagram of a wire. And you can see that I've given some specific descriptors for this wire. I know how long it is. One end is at x equals 0. One end is at x equals L. I'm going to go ahead and draw that on our picture here. So there is my wire, pretty long. And I know that this end here is at x equals 0, and this end here is at x equals L. Let me fill those pieces of information in here. And I want to start out by sketching a charge diagram on the wire. So I want to show basically where is the charge on this thing. So I'm going to use little pluses and minuses to indicate charge. I'm going to assume that the charge on this wire is positive. And it's uniform, which means that each charge is going to be separated from the adjacent charge by the same distance. I think I'm succeeding at that. That looks pretty good. So now I've got a uniform charge density picture. I'll adjust that a little bit. And you can see again, each charge is the same distance from both of its neighbors as all the other charges are. So that's a charge diagram there. And now I want to find what the charge density is. I want to know what is lambda equal to here. So let's see. Do I remember the code for lambda? I do. So lambda here is going to be the total amount of charge, which I've called Q0, divided by the total length of the wire, which is just capital L. So there I have it. That is the charge density for a uniformly charged wire. Relatively straightforward there. All right. Now, the question may have jumped into your head. Well, wait a second. What if the charge on the wire is not uniformly distributed and I'm not allowed to do that? That's a good question. And the thing that I can do is I can instead calculate the charge density as a local quantity. So I'm going to draw a picture of a different wire now that has a non-uniform charge density. I'm going to go ahead and put maybe a whole bunch of positive charge at one end, and then it starts getting more and more spread out as I get to the other end. And then maybe it even switches and it's negative after a while. Something like this. This would be a perfectly reasonable charge density. It looks like I went off the size of the thing. I'll delete a couple of charges there. So there's a non-uniform charge density. Now I definitely can't just take the total charge and divide it by the length, because as you can kind of see, there's more charge located at some places and there's less charge located at other places. So this charge density is going to be a function of x, right? Depending on where I am along the wire. If you tell me x, I can tell you what the charge density is. And the way that I can do it is by using the same strategy. Take the total charge on a small piece of the wire and divide that charge by the total length of that small piece. This is kind of some calculus reasoning, and you'll see that I use the letter D, which is the calculus letter that means take a small amount of. So if I were, for example, to say I want to know what the charge density is on that little piece there, I can look and see how much charge is there on that little piece, right? So dq, and then how wide is that little piece, dx, and I can divide those things. And I'm going to get a different answer for that ratio, depending on whether I'm over here at this end, where there's a lot of charge in any given centimeter, versus over here, where there's not that much charge in any given centimeter. And that all is going to be still different from what I get over on the far right-hand side, where I've got some negative charge for each centimeter. So it's something you always want to calculate locally if you're in a non-uniform situation.